Hi everyone. Today we'll be discussing the LeetCode problem of the day, count unguarded cells in the grid. So you're given two integers m and n representing a zero indexed grid, m cross n grid. And you're also given 2D integer arrays, guards and walls, where in guards you have row and column, and in walls 2D array, you have row and column of the walls, which represents the position of the ith guard and the jth wall. So a guard can see every cell in all four directions, north, east, west, south, starting from their position, unless obstructed by a wall or another guard. So a cell is guarded if there is at least one guard that can see it. So you have to return the number of unoccupied cells that are not guarded. So in this example, we have few guards here and few walls. So for the first guard, his vision will go. Let me use a different color. So his vision can go all the way till the last row in this direction. In the left and top, cell is out of bound, and in the right there's a wall. So this guard will guard all of these cells. So they are marked in red. So for the next guard, he'll guard these cells and this, and here his vision stops because there's a wall here. So he can't guard this wall. I mean this cell. And his vision goes bottom also, and he'll guard all these cells. And finally, for the last guard, this way, top, and then bottom. So after this, we can see that we have few cells that no guard is watching. So in this case, we have 1, 2, 3, 4, 5, 6, 7. So 7 cells are unguarded. So we just have to return the count of the unguarded cells, which is 7. And if you see the second input, here we have one guard, and he can watch in all four directions, but there are walls in all four directions. So these are the unoccupied cells which are unguarded, and the count is 4. So we return 4. And coming to the constraints, we have both either m or n can be up to 10 power 5, but it is guaranteed that m cross n will be only 10 power 5. So that means if m is 10 power 5, then n will be only 1. And if m is 10 power 4, then n can be only up to 10, because the whole grid m cross n should be less than or equal to 10 power 5. And the guard's length and the wall's length is less than or equal to 5 into 10 power 4. I mean, he's mean to say the count of the walls and guards is less than this. And obviously, this will be less than or equal to the total size of the grid, because guards and walls can't exceed the total number of cells in the grid. And guards of I dot length and walls of j dot length equal to 2. So this is a 2D array representing the guards and the walls. So here we have some rows and always 2 columns, because this is the x coordinate and this is the y coordinate of the first guard, and same with the walls. And finally, the row I and row j is less than m. So he's denoting this. This is the row I, row j. I mean, row I, and this is the row j. This is the column I and the column j. So all of them should be less than or equal to the grid, the original grid. And it's also mentioned that all positions in guards and walls are unique. So there's no repetitions in this list. Now let's go with the approach. So we are given number of rows and number of columns. So with that, we can create a 2D grid in that we can mark whatever the cells are guards, walls, or the unguarded cells. So first we'll create a m cross n grid, which will have all zeros. So here 0 will denote empty cell. And once we do this, we'll iterate on the guards array, and we will mark all the guards in this grid. So in the guards array, we have 3 guards at position 0, 0. So wherever we have a guard, we'll just mark the cell as 1. So 0, 0 is 1, and 1, 1 is also 1. and then 2, 3. This is also a guard. So in this array, in this grid, we have marked all the guards with the value 1. And similarly, we'll do it for the walls. So for the walls, we will maybe pick a number 2. And I think this is also a wall. So it's a 2. And this is also 2. So this is the initial configuration. And whatever the zeros are there here, those are the unguarded cells. So initially. And we can get the count by doing n into m minus this guard length minus walls length. So this means n into m will give us the whole grid size, which is 6 into 4, 24. And out of 24, we have 3 guards, and also we have 3 walls. So initially we have 18 cells which are unguarded. So that means we have 18 zeros. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So initially we'll keep a count track of unguarded, and that will be 18. And we'll just start the simulation. We'll go to each guard, and for that guard, we will, suppose we have a guard here, we will travel top, bottom, left, right in all directions. And whenever we find an empty cell, we'll convert it into a guarded cell, and we'll just reduce the unguarded count. So it's just like a simulation for all the guards. So let's see how we can do that. So yeah, so once this is created, we'll just iterate on the guards array, which is this array. So first we are at guard 0, 0. We'll first iterate to the top. So when you go to the top, so guard 0, 0 is here. When you go to the top, it's going out of bound. So you stop. And now you try to move to the left, and left also it's out of bound. Now when you try to move to the right side, so right side, that's a wall. So again you stop. And finally, when you try to move to the bottom, you see that there's a unguarded cell. So first you mark it as a guarded. For guarded, we can just put it as a 3. And since we have converted one unguarded cell to a guarded, we'll just reduce the value of this unguarded cells by 1. And we'll keep moving in this direction. So this also will convert it to 3. This also will be converted to 3. And this also will keep decreasing, and so on. So we'll do this process until his view will go out of the array, or either it is obstructed by a wall or a guard. So this is the simulation for the first guard, and our unguarded cells is 15 so far, because 3 of these unguarded cells have been converted. Let me just write it properly. So next we will start with this guard. When he tries to go to the top, it's a wall, so he stops, and he'll try to go to the left. So left, it's a 3, which is guarded. So we won't decrease this value because it's already converted. We no need to convert it again to unguarded cell. So he goes to this cell, then again he'll move to the left, and since it's going out of bound, so he stops in this direction. Now he'll move to the bottom. The bottom, there's a 0, so he'll convert it to a guarded cell. So this will be 3, and this will be reduced by 1. So this is 14. Again he'll move to the bottom. This will be converted to 3. Then this is 13. And he'll go to the bottom, and it's out of bounds, so he stops. And finally, for this cell, he'll move to the right direction. So right hand side, this is a 3. So this reduces by 1, it becomes 12. Again, he goes to the right. This is also unguarded, so he turns it into a guarded cell. and reduces the count of the unguarded cells. And then again, next here you can see that 2 is a wall, so the process stops. So this guard is also processed completely. Finally, let's process the third guard. So here, if we wants to move to the left, it's a wall, so he stops. And if he wants to go to the bottom, he'll go to the bottom. This is an unguarded cell, so he'll mark it as guarded and reduce the unguarded count. So this will be 10. And when he goes down, it goes out of bounds, so he stops. And now in the right direction, here it's a 0, so he converts and reduces the count. This is 9. Again he goes to the right, so again he found a 0, so it will be marked as guarded and count will decrease. And here out of bounds, so it stops. Finally, we are left with the top direction. So he'll go to the top. So top, it's already guarded, so he won't reduce the count again. Then again he'll move to the top again. It's a 0, so he'll convert it and mark this as 7. And again he'll go to the top and it's out of bounds, so he stops. So when this process ends, we see that we are left with answer equal to 7, which is same as the number of unguarded cells in our grid. So we have 1, 0, 2, 3, 4, 5, 6, 7. So we'll just return whatever the unguarded value is, which is 7. So the approach is pretty simple. We just have to do a simulation for all the guards and just mark the values properly. Also, you can have a question that suppose there's a guard here and here there's a guard, and suppose this is a grid. So when you process this first guard, his view goes like this, this, and this. So all these cells, he will guard it. Now when you are iterating, you're simulating for this guard, you will again process this way, this way, this way, and again the top. So you can say one thing that this cells is already guarded, so why am I iterating on that again? So won't it be a duplicate? So in this case, yes, it will be a duplicate. This path is already guarded, but again this guard will go and check whether it is guarded or not. So it is important to check because of the cases like this. So suppose we have a guard here and we have a guard here. So in this case, let's see what happens. So this guard has a view like this, and this. And for this guard, he'll check this direction, and he'll keep checking this direction. And we can see that this cell is guarded. So we can't stop here because the top part is not guarded. So even though in our path we find there's a guarded cell, we should keep proceeding until we find a guard or a wall, or until we go out of bound. So we should also check beyond this whether all these cells are guarded or not. And the same thing here, even though here all the cells are unguarded, but here we see this cell is guarded. So we should not stop here. We should proceed further because here we can see we still have few unguarded cells which need to be guarded. So this we should just keep it in mind. So the only thing is this guard's view keeps moving until he either finds a wall or he finds a guard or he goes out of the cell. Now let's code the approach we just discussed. So first I'll be creating a 2D list, 2D grid. And we have m rows and n columns. And we can also count the number of unguarded cells, which will be n into m minus guard.length minus walls.length. So initially we have these many unguarded cells, and when we do the simulation of all the guards, the final value will just return that. So first let's iterate on the guards array and mark all the guards in this grid. So I can say guard in guards. Grid of the X position, you can get it by guard of 0, and the Y position, guard of 1. So for guards, we are trying to mark it with value 1. And for walls, we will mark it with 2. Wall in walls. Yeah. So we have marked all the guards and all the walls with 1 and 2. So once it's done, let's just iterate on the guards. So we have to do the simulation on the guards, right? So we'll iterate on the guards list, guards array. And for each of the guard, we'll move top, bottom, left, right. So we'll iterate until we go out of bound or we see a wall or a guard, like we discussed. So for iterating on all 4 directions, we can use a directions array, because suppose there's a guard at x comma y. So to move to the top, your x coordinate will decrease by 1 and the y coordinate remains same. To move to the bottom, your x coordinate will increase by 1, y coordinate will remain same. And for the left, x will remain same, y coordinate will be minus 1. And to the right, your x coordinate remains 0, y coordinate will increase by plus 1. So with the starting x comma y, to this, when you add this, it means you are moving to the top. So initially you have x comma y, then you will have x minus 1 comma y. That means you are moving to the top. So again, when you add this value to this, it will be x minus 2 comma y. So from this we can see that continuously if we keep adding this value to our x and y, it is same as moving in the top direction. And similarly, continuously if we keep adding these values to our x and y, it is same as moving in the right direction. So we can use all these things to simulate in what direction we want to move. So for that, let me just create a directions array. Directions equal to, so first we'll have minus 1 0, which is the top direction, 1 comma 0 is the bottom, and 0 comma minus 1, which is the left direction, 0 comma 1, which is the right. So for each particular guard, we want to iterate on all 4 directions. So we'll just iterate on the directions array. And I equal to 0, I less than 4, I plus plus. So currently our x will be guard of 0 and y will be guard of 1. So we have the first guard, which is at 0 comma 0. So on this guard, we will iteratively add this value minus 1 comma 0, so that this position, his view will move to the top. So we should iteratively add this until it goes out of bound, or like the checks we have discussed, until it goes out of bound, or until you encounter a guard, or until you encounter a wall. So you can say that while x is greater than or equal to 0 and x is less than m, which is the number of rows, and y is greater than or equal to 0, y is less than n, which is the number of rows, and grid of xy is not equal to 1. That means it's not a guard, and grid of xy is not equal to a wall. So these 4 conditions representing that this position is inside the grid, and this is indicating that this particular cell is not a guard, and this is indicating that the particular cell is not a wall. So if all of these are true, then we can say that this particular cell is guarded. So first we'll check if it's really an unguarded cell. So if grid of xy equal to 0, that means it's an unguarded cell. So we'll convert it to a guarded cell. So we can say grid of xy, we'll mark it as 3, and we'll reduce the unguarded count by 1. And after that, since we want our simulation to run, in x, we'll add directions of I 0, and in y, we'll add directions of I 1. So directions of I 0 and directions of I 1, in the sense, first these values will be added to our x. So when this value gets added, like we discussed, it'll keep moving to the top. And when this value gets added, so x always increases by 1 and y always increases by 0. That means it is same as moving to the bottom direction. So this is the simulation. We'll run the simulation as long as all these conditions are met. And initially also we have to start with that direction, because initially the particular x and y value is a guard, so this condition will fail. So you have to start the iteration with one value. Which I mean to say, if you are at this guard, suppose you are here and you are in this iteration, that means you want to move to the bottom. So initially you will start with x equal to guard of 0 plus direction of I 0. So you will start with x equal to 0 plus 1, y equal to 0 plus 0. So which means you will start at 1 comma 0. So that means you will directly start at this point. And from there, at each step, your x is increasing by 1 and y is increasing by 0, because here you have 1 comma 0. So you will cover all these cells, and at some point you will go out of the bound. So this is the simulation, and once the simulation is done, whatever the unguarded value we have, we just return it. We just return, yeah. We test it. Okay, what's the issue? It is guards.length. Okay, let me submit. Yeah, and it works. Now let's do the time and space complexity analysis. So the time complexity is a bit tricky. So for a particular guard, we are iterating top, bottom, left, and right. So at max, for a particular guard, we are iterating top and bottom. So he can cover the whole row. So total m iterations, and he can also cover left and right. So he can cover all the columns, which is n, and n is the number of columns. So this is the average time complexity for a particular guard. And since we can have guards less than or equal to m into n, so we can argue that the total complexity is this into m into n. So this is the complexity it might look at starting, but that's not true. Even we can see this complexity will go out of bound, because m into n is only 10 power 5, and to that if we multiply either m or n, and that can also be 10 power 5, so this will go total 10 power 10. So this is not the actual complexity, since we have few checks that a guard will only go until he finds a wall or until he finds another guard. So because of that, the complexity reduces drastically. So let's see what the actual complexity is. So suppose we have a column like this, and in this column we have few guards, and suppose there's a guard here. So for the first guard, his view goes this way, and top, left, and right. For the second guard, his view goes like this, and top, bottom, left and right. For this third guard, again top, bottom, left and right. For the fourth guard, again it goes to the top, bottom, left and right. So here we can see that this particular column is being traversed twice. We can see here all these cells are being iterated twice, here also twice, twice and twice. So we can say that this particular column is traveled 2 times in total. So we have 2 into how many elements we have in this. This is equal to number of rows, which is n, and we have m such columns, so total m. Sorry, the number of elements in this is m, because m is the number of rows, and we have total n columns, so total 2 into m into n. So this is what we do. We iterate on this top to bottom direction. And similarly, let's see to the left and right. So if we have something like this, and we have a guard here, 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 and same thing we can argue this guard's direction like this, like this. So each of this cell in this particular row will be iterated twice. So again, we can say that we have 2 into the number of columns, which is n, and total we have m such rows. So this is the complexity in this direction, horizontal direction. So if we add both of them, we will get the total complexity as 4 into n into m. So this is the total complexity. And if we see n into m is up to 10 power 5, so 4 into n into m will be in the limits. So overall, we can say that the time complexity is order of n into m, since we can ignore the 4 because it's a constant. And for the space complexity, we are creating a 2D grid. So because of that, space complexity will also be order of n into m. And the directions array, it's only a size 4 into 2, so we can just ignore this. I also have the code in Python. If anyone wants to view it, I'll add it in the description as well. And let's catch up in the next video.